Black holes are one of the most mysterious and intriguing phenomena in the universe. They are the result of the gravitational collapse of massive stars and are so dense that their gravity prevents even light from escaping from their boundaries. Therefore, they are black and invisible to our eyes, although their presence can be felt through their environmental impact. They occur when a massive star exhausts the fuel needed to sustain nuclear fusion. The star begins to collapse under its own weight, contracting to such a density that a point with an infinite curvature of spacetime called a singularity is formed. The singularity is surrounded by the event horizon, an imaginary boundary beyond which nothing can escape. The event horizon is a kind of threshold that separates the black hole from the outside world. The nature of black holes is studied thanks to Albert Einstein's general theory of relativity. The theory predicts that the mass of the black hole warps spacetime, forming a gravitational well. This deformation is so strong that it affects the trajectories of light and matter. For example, light passing near a black hole can be warped, forming an effect known as gravitational lensing. There are several types of black holes depending on their mass. Stellar black holes are formed by the collapse of massive stars and have a mass that is usually 3 to 10 times the mass of the Sun. Supermassive black holes are found at the centers of galaxies, including our own Milky Way. Their mass reaches millions or even billions of solar masses. Their origin remains a mystery, but they are thought to form due to the merger of smaller black holes and the absorption of matter over billions of years. Another category is intermediate black holes, which have masses ranging from a few hundred to several thousand solar masses. Their presence has only recently been confirmed thanks to modern observational methods, such as gravitational wave astronomy. The phenomenon of Hawking radiation adds another mystery to the nature of black holes. Stephen Hawking predicted that black holes are not completely black, they can lose mass and energy due to quantum effects, emitting weak thermal radiation. This phenomenon is explained by the interaction of particles and antiparticles at the event horizon. A single particle can fall into a black hole and the other escapes, causing the black hole to gradually evaporate. Space traps are also a place of extreme phenomena. If we imagine that an object falls into a black hole, it undergoes a phenomenon known as spaghettization. This is due to the difference in gravitational forces between the near and far sides of the object. Gravity is so strong that the object stretches into a long and thin thread. The study of black holes is carried out using various methods. For example, telescopes capture the X-ray radiation that is produced when gas and dust are heated to extreme temperatures before falling into a black hole. Gravitational waves are also used, fluctuations in spacetime caused by collisions of black holes. In 2015, for the first time, such waves were recorded, which was a revolutionary discovery in physics. These objects can interact with other objects in the universe. For example, they are able to absorb stars that pass too close, forming powerful accretion disks of matter orbiting the event horizon. In such cases, there is an emission of relativistic jets, jets that spread over thousands of light years. However, these cosmic craters are not only destructive. They may also play a key role in galaxy formation. Supermassive dark zones in the centers of galaxies regulate the processes of star formation, influencing the distribution and movement of matter. This relationship between black holes and galaxies is one of the most pressing topics in modern astrophysics. Gravitational collapse objects are also important for studying the fundamental laws of nature. They are laboratories for testing relativity, quantum mechanics, and their interactions. For example, the problem with the information paradox is that quantum mechanics requires the conservation of information, while general relativity assumes its annihilation in a singularity. This question remains unresolved and is one of the key mysteries of physics. The phenomena of space and time capture the imagination of not only scientists, but also a wide audience. They inspire science fiction, where they are often depicted as gateways to other dimensions or time machines. And although these concepts are hypothetical, they stimulate interest in the study of the universe. In 2019, the world saw for the first time a photograph of a black hole taken by the Event Horizon Telescope. This image was a confirmation of the theory of relativity and demonstrated the power of modern technology. Dark gravitational forces remain one of the most intriguing objects in space. Studying them opens up new horizons for science, helping us better understand the nature of the universe and our place in it. An incredible source of inspiration and research, so it is worth delving even further into aspects of their impact on space, physics, and our understanding of reality. One of the most interesting topics in the study of black holes is their effect on the surrounding matter and radiation. When material, such as gas, dust, or even a star, falls into the gravitational field of a black hole, it does not immediately disappear into the singularity. Instead, matter forms an accretion disk, a structure that consists of heated gas orbiting a black hole. Due to friction and gravitational forces, the gas in this disk heats up to millions of degrees, emitting energy in the X-ray spectrum. It is this radiation that makes black holes visible to astronomers, because they themselves do not emit light. Supermassive black holes, which are located at the centers of galaxies, are often accompanied by powerful jets of high-energy particles escaping from poles of the accretion disk. These jets can reach thousands of light-years and significantly affect the galaxy's environment. For example, they are able to expel gas from the galaxy, slowing down or even stopping the process of star formation. Such interactions are an example of how black holes can influence the evolution of galaxies and the formation of cosmic structures. In addition, they can merge with each other, forming even more massive objects. The merger of these astronomical objects is accompanied by the emission of gravitational waves, which were predicted by Einstein in his general theory of relativity. In 2015, it was possible to register these waves for the first time, and this discovery was revolutionary. It not only confirmed the theory, but also opened a new era in astronomy, the era of gravitational wave observation. Another intriguing topic related to these objects is their formation and growth. Although the process of stellar black hole formation is more or less clear, the origin of supermassive black holes remains a mystery. How did they reach such huge masses in a relatively short time after the Big Bang? There are several theories. One of them suggests that supermassive black holes form from seeds, primordial black holes that appeared in the early universe. Another hypothesis suggests that they grow by absorbing large volumes of matter or merging with other subjects of the astrophysical singularity. Even more exotic is the idea of primordial black holes, which could have arisen shortly after the Big Bang due to fluctuations in the density of matter. Such objects could have a variety of masses, including very small ones. If they exist, primordial black holes could explain some mysterious phenomena, such as the nature of dark matter, which makes up a large part of the mass of the universe but still remains elusive. The existence of these gravitational monsters poses numerous philosophical and theoretical questions to science. For example, is it possible to travel through a black hole? Theorists suggest that a black hole could be a portal to another universe, or even to another time. These ideas remain speculative, but they stimulate scientific research in the field of quantum gravity and the nature of spacetime. The paradox of information in black holes is another unsolved problem in physics. If an object falls into these space traps, all information about its properties seems to be lost when it reaches the singularity. However, quantum mechanics states that information cannot be destroyed. This contradiction has become one of the central questions in modern physics, and solving this puzzle could lead to a revolution in our understanding of quantum mechanics and gravity. Another mystery is the nature of the singularity, which is the central point of a black hole. In a singularity, the laws of physics that we know cease to apply. It is a place of infinite density and curvature of spacetime. Current theories such as quantum gravity and string theory try to explain exactly what happens in a singularity, but there is no definitive answer yet. These light absorbers also have a huge impact on popular culture. They are often depicted in movies, books, and video games as mysterious, dangerous objects, or as means of traveling through time and space. For example, in the movie Interstellar, the gargantua black hole became the centerpiece of the plot, and her image was created using real scientific models, making her one of the most accurate in cinema. In conclusion, black holes are not just mysterious objects that challenge our understanding of the universe. They are the gateway to new knowledge and understanding of how our space works. Studying them is not only a journey into the world of extreme phenomena, but also the key to unraveling the fundamental laws of nature that underlie everything that exists. Black holes remain the focus of attention of astrophysicists and theorists alike, because they open up limitless horizons for scientific research and reflection on the nature of reality. To further understand their essence, it is worth considering additional aspects, such as their connection to dark energy, quantum effects, as well as their role in the large-scale structure of the universe. One of the most exciting theories is the suggestion that black holes may be related to dark energy, a mysterious force that accelerates the expansion of the universe. Some current models put forward the idea that the vacuum energy that surrounds black holes could be a source of dark energy. If this is true, then these gravitational wells play a much larger role in cosmology than we can imagine. It also opens up opportunities for new approaches to solving one of the main mysteries of modern science: why is the universe expanding at an ever faster rate? The quantum aspects of black holes are one of the most active research topics. As mentioned, Stephen Hawking predicted that black holes emit energy through a process known as Hawking radiation. This process demonstrates the interaction of gravity with quantum fields and suggests that black holes can gradually lose mass and eventually evaporate. This phenomenon highlights the relationship between quantum mechanics and general relativity, but also reveals a deep contradiction between the two. These contradictions, known as the information paradox of black holes, stimulated the development of new theories, such as the holographic principle. This principle states that all the information that falls into a black hole is stored on its event horizon in the form of a quantum code. If true, then black holes could act as a kind of storage devices for information about the universe, which opens up exciting prospects for quantum physics. Objects with critical gravity not only destroy, but also create. They play an important role in the formation of galaxies and large-scale structures of the universe. For example, supermassive black holes can act as architects, forming galaxies through their gravitational interaction. Their ability to influence the movement of gas and dust around them creates conditions for star formation. In some cases, however, supermassive black holes can slow down this process if their jets cleanse the galaxy of the gas needed to give birth to stars. One of the most striking phenomena associated with black holes is relativistic jets, or jets. These jets are formed by extreme magnetic fields that are generated by accretion disks around rapidly rotating black holes. Jets contain charged particles that are ejected at speeds close to the speed of light. They are able to penetrate intergalactic space, affecting nearby galaxies and even creating shock waves in intergalactic gas. The study of jets helps scientists better understand not only the nature of black holes, but also the evolution of galaxies and quasars, extremely bright objects that gain energy from the accretion of matter onto supermassive black holes. And while black holes are often associated with destruction, they also open the door to ideas about traveling through space and time. In general relativity, the existence of so-called wormholes is allowed, hypothetical tunnels that can connect different points in spacetime. Although the existence of wormholes has not yet been confirmed, their study offers hope for the development of future interstellar technologies. Gravitational influence zones are ideal objects for testing new theories. They challenge our knowledge of high-energy physics, quantum fields, and gravity. Future research with advanced telescopes such as the Space Telescope James Webb, as well as new gravitational wave detectors, will allow you to penetrate even deeper into their nature. Black holes are not just dark spots on the map of the universe. They are the key to nature's deepest mysteries, from the beginning of time to the limits of space. Studying them not only expands our knowledge of the cosmos, but also raises fundamental questions about what it means to be part of this boundless and mysterious universe. One of the most interesting concepts is the idea that black holes can be energy sources capable of fueling the evolution of galaxies and even creating entire cosmic structures. The enormous amount of energy released during the accretion of matter exceeds the energy produced by stars, and this energy is capable of influencing the chemical composition and dynamics of gas in galaxies. This phenomenon, known as active galactic nucleus feedback, can stop star formation or change the ways in which new galaxies form. Quasars, one of the brightest objects in the universe, are an example of such processes. They are powered by the energy released during the accretion of matter onto supermassive black holes, and their brightness can surpass the glow of all the stars in the galaxy combined. Observations of quasars allow scientists to study the conditions that prevailed in the universe in the early stages of its evolution. Dark matter is another mysterious substance that makes up about 27% of the mass energy of the universe, but does not emit light, so it cannot be observed directly. Black holes are often seen as candidates for the role of reservoirs for dark matter. Although research has not yet provided definitive answers, there are theories that black holes can interact with dark matter particles, creating unique gravitational signatures. For example, if primordial black holes formed in large numbers in the early universe, they could be major components of dark matter. However, this idea remains speculative, since no clear evidence of the existence of such objects has yet been found. Observations of black holes that existed several hundred million years after the Big Bang raise questions about their origins. How were they able to reach such masses in such a short time? One possible answer is the direct collapse hypothesis. In this scenario, large clouds of gas could collapse directly into the black hole, avoiding the star formation stage. Another option is accelerated growth due to the efficient absorption of matter. The study of early black holes allows scientists to better understand the conditions that prevailed in the young universe, including the formation of the first galaxies and stars. Imagine two black holes orbiting each other, gradually getting closer. This process is accompanied by powerful gravitational waves, fluctuations in spacetime that propagate at the speed of light. When two black holes merge, they emit huge amounts of energy in the form of gravitational waves. The first such waves were recorded in 2015 by the LIGO Observatory, which was a revolution in physics. These events not only confirmed the existence of black holes and mergers between them, but also opened up a new way of studying the cosmos. Gravitational waves allow us to hear the universe, allowing us to study objects and phenomena that are inaccessible to conventional telescopes. One of the biggest challenges of modern physics is the unification of two fundamental theories, quantum mechanics and general relativity. Black holes are at the junction of these two sciences, which makes them ideal laboratories for developing new theories such as quantum gravity. For example, the question of whether information that falls into a black hole is stored remains a central problem in physics. If this problem is solved, we can get the key to a theory of everything that will unite all the fundamental interactions of nature. Even though black holes are associated with the end, they can also be the key to the future. There are ideas that the use of energy released during the accretion of matter can provide humanity with an almost infinite source of energy. Such ideas remain fantastic, but they highlight the importance of black holes in understanding not only the cosmos, but also our potential as a species. Compact massive objects continue to capture the imagination and raise questions. Not only are they objects of extreme physical phenomena, but they also make us think about deeper questions of being, such as the nature of reality, time and space. Studying them is a journey that never stops and leads us to discover new facets of the universe. Black holes are objects that never cease to amaze and delight with their mystery. They are the result of an extreme fusion of space and time, where the laws of physics that we know cease to operate in the usual sense. Their appearance requires the fulfillment of strict conditions, but this is what makes them so interesting to explore. A star that has exhausted its nuclear fuel survives a collapse to form an ultradense object with gravity capable of holding even light. This process occurs with the participation of gravity, which begins to prevail over all other forces, causing the matter of the star to contract to extremely small sizes. The result is a singularity, where the density and curvature of space become infinite. An event horizon forms around the singularity, a boundary beyond which even light cannot escape. This makes black holes invisible, but they leave traces in the space around them. Scientists learn about their existence due to the effect on nearby matter or radiation that occurs due to the heating of gas in an accretion disk. The temperature in such disks can reach millions of degrees, generating X-rays that can be recorded with modern telescopes. The study of black holes opens up the opportunity for us to look into the depths of space and time, because they have been formed over billions of years. One of the biggest discoveries in the study of these objects was the observation of gravitational waves caused by the collision of two black holes. These waves not only confirmed the predictions of general relativity, but also made it possible to look at the dynamics of the universe. Black hole mergers are events of colossal proportions in which energy equivalent to several solar masses is released. Some cosmic vortices reach masses that are millions or even billions of times the mass of the Sun. Such objects are called supermassive black holes. They are found at the centers of galaxies and are believed to play a key role in their formation and evolution. For example, our galaxy, the Milky Way, has a supermassive black hole called Sagittarius A* at its center, which is 4 million times the mass of the Sun. It influences the movement of stars and gas in its vicinity, forming the characteristic structure of the galaxy. The nature of dark gravitational forces remains the subject of numerous theoretical debates. For example, the Hawking radiation predicted by Stephen Hawking suggests that black holes can evaporate due to quantum processes at the event horizon. This discovery challenges our understanding of gravity and quantum mechanics, which seem to contradict each other under these extreme conditions. The theory suggests that a particle-antiparticle pair can occur near the event horizon. One of them can fall into a black hole and the other can escape, resulting in a loss of mass in the black hole. Another important topic is the information paradox of black holes. According to quantum mechanics, information about the state of any system must be stored, but general relativity predicts that all information that falls into a black hole disappears in a singularity. This contradiction has been the catalyst for the development of new theories, such as the holographic principle, which states that information is stored on the surface of the event horizon in the form of a two-dimensional holographic code. Black holes are also laboratories for testing the wildest hypotheses. For example, the idea that black holes can be gateways to other universes or even wormholes that allow travel through space and time. Although these concepts remain speculative, they open up new horizons for reflection on the nature of the universe. The abysses of space and time force us to rethink the fundamental laws of nature and expand the boundaries of our understanding of reality. Studying them not only allows us to look into the deepest corners of space, but can also lead us to revolutionary discoveries in physics that will change the way we see the universe. This is an endless journey that opens up new mysteries and challenges for us. Light absorbers are not only objects that challenge our understanding of physics, but also a source of inspiration for new discoveries. They appear on different scales, from stellar to supermassive, and their impact on the universe is enormous. Black holes can be the driving force of the evolution of galaxies, to influence the distribution of matter and energy in intergalactic space, as well as to suggest how the first structures in the universe were born. The merger of these stellar tombs was one of the most spectacular phenomena astronomers have observed. As two black holes orbit each other, they emit gravitational waves that gradually take away the energy of the system, causing the black holes to move closer to each other. Eventually, they merge to form a new black hole that may have a mass greater than that of both original objects. This process is accompanied by the release of an enormous amount of energy, equivalent to several solar masses, in the form of gravitational waves. These waves were first recorded in 2015 by the LIGO Observatory. This discovery not only confirmed the existence of black holes and gravitational waves predicted by Einstein, but also became the first direct evidence of the existence of a system of two black holes merging. Since then, dozens of similar events have been recorded, allowing scientists to study the properties of these exotic objects, as well as their role in the formation of the universe. Supermassive black holes at the centers of galaxies are the largest of the known types. Their masses reach billions of solar masses, and they have an enormous impact on the galaxies in which they reside. For example, the black hole at the center of the Milky Way, Sagittarius A*, is surrounded by clouds of gas and dust, as well as stars that orbit it at extraordinary speeds. Observation of these stars allowed scientists to accurately determine the mass of the black hole and its location. Some supermassive black holes create accretion disks from matter falling into them. These disks heat up to such temperatures that they begin to emit energy in the form of light and X-rays. This is how quasars appear, one of the brightest objects in the universe. The light we observe from quasars may be the result of events that occurred billions of years ago, making them a kind of lantern of the past. The existence of black holes also raises fundamental questions about the nature of time and space. The theory of relativity shows that the gravity of a black hole is so strong that time near it slows down. This phenomenon, known as gravitational time dilation, was demonstrated in the movie Interstellar, where characters experienced different time speeds due to the influence of a black hole. Even more exotic are the assumptions that black holes can be wormholes, tunnels that connect different points in space-time. Although this is still a hypothesis, such ideas make us think about the fact that black holes can be not only destroyers, but also pathways to new dimensions. Current research on black holes focuses on the combination of quantum mechanics and relativity, which is key to understanding what they are. Hawking radiation, for example, shows that black holes can gradually lose their mass and eventually disappear. This contradicts the idea of their absolute darkness, and indicates that even the most powerful objects obey the laws of quantum physics. Dark zones are mysteries that force us to rethink the limits of our knowledge and constantly ask new questions. They open the door for us to understand the deepest processes in the universe and, perhaps, one day will help us find answers to questions about the beginning of time, the nature of space and our role in this boundless cosmos. Black holes continue to amaze with their mysterious properties, and every aspect of their existence gives rise to new theories, hypotheses, and discoveries. One of the most interesting topics is their potential impact on the global evolution of the universe, as they may be related to many of the fundamental processes that shape the cosmos. Let's imagine the early universe, a few 100 million years after the Big Bang. The first stars to form were extremely massive and quickly exhausted their fuel. When such stars exploded as supernovae, their cores collapsed, creating the first black holes. These black holes may have become the building blocks for the supermassive black holes that are now located at the centers of galaxies. In the early universe, they could merge with each other, absorb matter, and gain mass rapidly. Black hole mergers may have played a key role in galaxy formation. The gravitational waves emitted during these mergers affect the distribution of matter in the universe, creating the large-scale structures we observe today. Supermassive black holes located at the centers of galaxies also control accretion processes, ejecting powerful jets that can clear galaxies of gas and affect the rate of star formation. The existence of supermassive black holes in the young universe is one of the great mysteries of modern astrophysics. How were these objects able to reach such huge masses in a relatively short time? One explanation is that the early universe may have had very favorable conditions for the rapid growth of black holes. For example, large gas clouds could directly collapse into black holes, bypassing the star formation stage. Another possibility is the extremely efficient accretion process, in which black holes absorbed huge volumes of matter. The cosmological role of black holes is not limited to their effects on galaxies. They can be related to the deepest aspects of fundamental physics. For example, there is speculation that black holes may have a connection with dark energy, which accelerates the expansion of the universe. Although these theories are hypothetical, they open up new avenues for exploring the relationship between gravity, quantum mechanics, and cosmology. Black holes also change our understanding of time and space. In the vicinity of a black hole, time slows down so much that, from the perspective of an outside observer, an object falling into a black hole appears frozen on the event horizon. This phenomenon is a consequence of extreme gravity, which warps the structure of spacetime. In theory, black holes can even serve as portals to other regions of the universe or alternate realities, although these ideas remain speculative. Modern technology allows us to study black holes with unprecedented precision. In 2019, humanity saw the shadow of a black hole for the first time thanks to the Event Horizon Telescope project. This achievement was a confirmation of the predictions of general relativity and showed how far our technology has advanced. In the future, similar projects, together with gravitational wave observatories such as LIGO and Virgo, will allow for even deeper study of these objects. Despite all the advances, black holes remain a mystery that provokes new questions. What happens inside the event horizon? How to combine quantum mechanics and gravity into a single theory that will explain their behavior? Is it ever possible to use black holes for interstellar travel? The answers to these questions can not only change our idea of black holes, but also help unlock the deeper mysteries of the universe. Black holes are objects that force us to push the boundaries of understanding, go beyond ordinary thinking, and look for new ways to explore space. They are the gateway to the deepest questions of science, and their study will undoubtedly continue for many centuries to come, opening up new horizons for us. These extreme masses remain some of the most mysterious and unexplained objects in the universe, and every aspect of their existence is full of mysteries. The deeper we dive into their nature, the more questions arise. Black holes force us to revise the fundamental laws of physics, opening up new horizons for research. One of the most intriguing aspects is the process of their formation and evolution. Stellar black holes form after the death of massive stars, when their cores collapse due to gravity. But how to explain the existence of supermassive black holes, the mass of which is millions or even billions of times the mass of the Sun? Their rapid growth in the early universe indicates that we do not yet understand all the mechanisms of their formation. Some theories suggest that they arise due to the direct collapse of giant gas clouds, others point to the possibility of absorption and merger with other black holes. Interestingly, there are assumptions about the existence of primordial black holes, objects that formed shortly after the Big Bang. Such black holes could have arisen due to fluctuations in the density of matter in the early universe, and their masses can range from very small to gigantic. If primordial black holes do exist, they could explain many mysteries, including the nature of dark matter. Dark matter remains one of the greatest mysteries of modern science, because it makes up a large part of the mass of the universe, but its nature is still unknown. Black holes also challenge our understanding of time. The theory of relativity shows that near a black hole, time behaves differently than under normal conditions. To an external observer, an object approaching the event horizon appears frozen in time. In the black hole itself, all the laws of physics cease to operate in the usual sense. This raises numerous theoretical questions, especially about what exactly happens in the singularity. A singularity is the point where the density of matter and the curvature of spacetime become infinite. General relativity cannot describe what happens under such conditions. This is where science needs new tools to describe reality, such as quantum gravity. Theorists, particularly string theorists, are working to create a model that could combine quantum mechanics and general relativity to explain the nature of the singularity. Space monsters also raise philosophical questions about the nature of information. According to quantum mechanics, information about the state of any system must be stored. But if an object falls into a black hole, that information appears to disappear into the singularity. This contradiction, known as the black hole information paradox, is one of the biggest problems in modern physics. Solving this paradox can help create a unified theory that unites all the fundamental forces of nature. Black holes not only cause theoretical controversy, but are also the objects of active observation. Telescopes such as the Event Horizon Telescope allow you to probe the event horizons of black holes and create their first images. These are incredible technological advances that demonstrate how far science has advanced. For example, a photograph of a black hole in the galaxy M87 showed not only the shadow of the event horizon, but also confirmed Einstein's predictions about the behavior of light in an extremely strong gravitational field. In addition, observations of gravitational waves from black hole collisions have ushered in a new era in astronomy. These waves are a kind of vibrations of space-time, and their study allows us to study the universe in a way previously inaccessible. They help detect black holes that cannot be seen by other methods and expand our understanding of their properties and distribution in space. Black holes also raise questions about potential interstellar travel. The idea that a black hole could be a gateway to another universe or to another part of our universe captures the imagination of not only scientists, but also science fiction writers. Although such concepts remain speculative, they stimulate interest in basic research. These objects not only reveal the mysteries of the universe, but also make us wonder about our own role in it. Black holes are a kind of windows to the extreme limits of reality, and their study expands our understanding of time, space, and existence itself. They are a challenge for science, but at the same time a source of inspiration that moves us forward towards new discoveries and a deeper understanding of the universe. Black holes are real space monsters that are both frightening and fascinating. Their nature is so amazing that at times it seems as if we are dealing with fantastic creatures, and not with objects of the real universe. However, they exist, and their impact on the surrounding space is so extensive that it can be felt even thousands of light-years away. Imagine a black hole lurking in the center of a galaxy. Its mass is millions of times greater than the mass of the Sun, and it, like the heart of a galaxy, affects all the processes around. The stars orbit it at breakneck speeds, as if dancing in a gravitational vortex. It is almost invisible, but its presence cannot be ignored. Matter approaching the event horizon begins to heat up to millions of degrees, emitting bright X-rays. It's like the death cry of a substance that is about to disappear forever. Even more stunning are supermassive black holes, which create huge jets of matter and energy escaping at speeds close to the speed of light. These jets reach thousands of light-years and are capable of affecting entire galaxies, changing their structure and dynamics. They give the impression that a black hole is a kind of engine that controls the evolution of space systems. However, even these phenomena seem simple compared to what can happen inside a black hole. What does a singularity hide? Is it really a point of infinite density? Maybe this is not the end, but the beginning of something completely different. Some scientists suggest that there may be other universes inside black holes, separated from our event horizon. Imagine that each black hole is a kind of eastern point to the new universe, which has its own laws of physics, time and space. Black holes also pose questions about the limits of reality. If we imagine that a person enters a black hole, his body is subjected to the phenomenon of spaghettization. This sounds almost ridiculous, but is actually the result of an extreme difference in gravitational forces between the near and far sides of the object. A person will stretch into a long, thin thread, turning into something completely unreal. But what's next? Will it disappear forever? Will it turn into energy? Or maybe leave some kind of trace in the very structure of the black hole? Equally intriguing is the idea that black holes may be the key to unraveling the nature of time. Time, as we understand it, behaves very differently near a black hole. Imagine that to an outside observer, an object falling into a black hole would freeze at the event horizon. But for the object itself, time will keep moving. How is this possible? This surprising behavior of time makes us wonder if a black hole could be some kind of natural mechanism for time travel. Now imagine that humanity will learn to use black holes in the future. For example, their gravitational energy can be a source of energy that surpasses all modern ideas about power. Black holes could serve as space engines that help ships travel between stars. Although it sounds fantastic, such ideas have been discussed many times within the framework of interdisciplinary research that combines astrophysics, engineering and futurology. However, black holes are not only about energy and destruction. They are a kind of keepers of time and space. They show us that our universe is much more complex and amazing than we can imagine. Studying them is not just a science, but a journey to the deepest corners of reality, where we are faced with questions that touch on the very essence of being. Black holes are a symbol of infinity, the unknown and the unknown. They remind us that even in the world of science, where it seems that much is already known, there are always secrets worth exploring. It's not just about space, it's about ourselves, our ability to dream, explore, and seek answers to the most difficult questions the universe poses to us. Black holes continue to be a kind of gateway to the unknown, reminding us that even in the world of modern technology and enormous advances in science, there are limits that we have not yet overcome. They challenge our imagination, force us to rethink the basics of physics and constantly open up new horizons for research. One of the most exciting ideas is that black holes could serve as sources of information about the early universe. Due to the fact that they are able to accumulate matter and absorb light, black holes become a kind of archives that store the history of the development of the cosmos. For example, observing supermassive black holes at the centers of distant galaxies allows scientists to get an idea of what the universe looked like billions of years ago. The light we see from these objects can travel to us for millions or even billions of years, revealing to us a picture of the distant past. Moreover, black holes help us understand the processes that occur on large scales in the universe. For example, when a black hole absorbs matter, it not only eats it, but also releases colossal amounts of energy in the form of radiation and jets. This radiation can accelerate the surrounding gas, creating huge cavities in intergalactic space. These cavities are part of the large-scale structure of the universe, which resembles a web, where galaxies and clusters of galaxies are connected by filaments of dark matter and gas. Dark zones also pose us with the question of whether there is a limit to knowledge. The singularity, which is at the center of the black hole, is where all the known laws of physics cease to apply. It is the zone where the density of matter becomes infinite and the curvature of spacetime reaches its limits. For it is almost unimaginable for us humans. We are used to ideas about causality, the clear passage of time and spaces that can be measured. But black holes indicate that there are regions of reality that do not yet lend themselves to our understanding. This is where the need arises to create a theory of everything, a model that would combine quantum mechanics and general relativity. Both of these theories are extremely successful in their fields, but when we try to apply them to black holes, they come into conflict. For example, quantum mechanics requires the preservation of information, but general relativity allows it to disappear in a singularity. This fundamental contradiction, known as the black hole information paradox, is one of the most important problems in modern physics. Another important aspect is Hawking radiation. The theory proposed by Stephen Hawking predicts that black holes are not completely black. Due to quantum effects at the event horizon, black holes can emit energy and even lose mass. Ultimately, this can lead to the complete evaporation of the black hole. But what is left after that? Will the information trapped in the black hole remain, or will it disappear forever? This question remains open. Gravity wells are also a source of inspiration for finding new ways to explore the cosmos. The gravitational waves that occur when black holes merge have opened up a whole new field of astronomy. These waves allow you to hear the universe, observe phenomena that cannot be seen with conventional telescopes. For example, the merger of two black holes can create a signal that allows you to determine their mass, distance, and even place in space. This is a new way of research that complements traditional methods and opens up new horizons for science. In the future, as technology becomes even more advanced, we will be able to look even deeper into the nature of black holes. For example, next-generation space telescopes will be able to study event horizons in detail and study processes that occur in the most extreme conditions. Perhaps one day we will even be able to create artificial black holes for research in the laboratory, which will help us better understand the fundamental laws of nature. Black holes are not only objects to study, but also philosophical symbols. They show us that even in the darkest corners of the universe, there is something worth exploring and discovering. They force us to expand the boundaries of our understanding and never stop in search of the truth. It's a reminder that science is a never-ending journey, and each new discovery only opens the way to even bigger questions. Objects with critical gravity remain in the spotlight as some of the most intriguing objects in the universe. They demonstrate that space is a place where the boundaries of our knowledge are blurred and opportunities are expanded. Their unique properties raise many questions that only stimulate our imagination and thirst for exploration. One of the most exciting topics is the interaction of black holes with their environment. Imagine a supermassive black hole at the center of a galaxy absorbing huge volumes of gas and dust. This creates a powerful accretion disk where matter rotates at incredible speeds, heating up to millions of degrees. The radiation that occurs in this process can be so strong that it can be seen from a distance of billions of light-years. Such objects are called active galactic nuclei, and they are among the brightest light sources in the universe. Active galactic nuclei sometimes give rise to relativistic jets, narrow jets of high-energy particles that are ejected at speeds close to the speed of light. These jets can extend thousands or even millions of light-years, affecting the intergalactic medium. They blow gas out of galaxies, inhibiting the formation of new stars, and can create huge cavities in the cosmic web, the structure of the universe made up of galaxies and clusters of galaxies connected by filaments of dark matter. But black holes aren't just destroyers. They can also play the role of creators. Their influence on the gravitational field and the distribution of matter can contribute to the formation of new structures in the universe. For example, the interaction between a supermassive black hole and the surrounding gas can trigger processes that contribute to the formation of new stars in galaxies. This makes black holes a kind of conductors of the cosmic symphony. Another surprising aspect of black holes is their potential as energy sources. The gravitational energy that is released when matter falls into a black hole can be much more efficient than nuclear fusion, which powers stars. This opens up fantastic prospects for future interstellar civilizations. If humanity is ever able to learn how to harness the energy of black holes, it could be a solution to the problem of energy resources. Imagine a future where giant space stations orbit a black hole, harvesting its energy. Such a concept, known as the Penrose sphere, is based on the theory that particles that fall into the relativistic field of a rotating black hole can release energy. Although this remains in the realm of fiction for now, ideas related to black holes inspire the development of innovative approaches to solving global problems. No less fascinating is the effect of black holes on time. Near a black hole, time for an outside observer almost stops. This curvature of time opens up surprising prospects for exploring its nature. Perhaps in the future, humans will be able to use black holes for time travel, although for now it feels more like fiction than scientific reality. But even today, black holes make it possible to study gravitational time dilation, which is important for testing general relativity. Black holes can also shed light on the nature of dark matter and dark energy. Some scientists suggest that primordial black holes that originated in the early universe may be part of dark matter. In addition, there are hypotheses that black holes may be associated with dark energy, a force that accelerates the expansion of the universe. While these ideas are speculative for now, they indicate that black holes may be the key to solving the biggest mysteries of cosmology. Black holes not only demonstrate how amazing and complex our universe is, but also show that there are no limits to cognition. They remind us that each new discovery opens up even more questions. In every corner of space, even in its darkest and scariest parts, there is always something worth exploring. This research is ongoing. Each new look at a black hole opens up new horizons for us and makes us think about what else we don't know. Perhaps black holes hide not only the answer to questions about the nature of the universe, but also a clue about our place in it. They are a challenge, an invitation, and an inspiration for everyone who tries to understand this boundless and mysterious cosmos. Black holes are an eternal mystery that lurks in the depths of space, forcing us to rethink the boundaries of reality. Their influence is so fundamental that they can be considered not only part of the cosmic landscape, but also key players in the development of the universe. Each black hole is a place where the deepest laws of physics collide, where gravity, space, and time merge into something unfathomable. Imagine a black hole slowly engulfing a star that has come too close to its event horizon. This process looks incredibly dramatic. The heated gas from the star forms a bright accretion disk that glows in the X-ray range. Some of this matter is emitted in the form of powerful jets that spread out thousands of light-years in space. But the rest of matter irrevocably falls beyond the event horizon, disappearing from our gaze. It becomes part of a black hole, increasing its mass and changing its rotation. The rotation of a black hole is another surprising feature. Black holes don't just absorb matter, they can have a colossal angular momentum that occurs due to the rotation of matter falling on them. Rotating black holes, called car black holes, create special effects in the space around them. For example, they cause the phenomenon of dragging space, when the very structure of spacetime rotates along with the black hole. This leads to incredible effects, such as curvature of the trajectories of light and matter passing nearby. Even more intriguing is that black holes can evaporate due to Hawking radiation. This process is very slow for massive black holes, but for smaller black holes, it can be significantly faster. For example, if primordial low-mass black holes formed in the early universe, they could have evaporated even before how we will be able to detect them. But what remains after the black hole has completely evaporated? Is information about the objects it has absorbed stored? Could this process be the key to understanding quantum gravity? The information paradox of black holes is one of the biggest problems of modern physics. It arises because quantum mechanics requires the conservation of information, and general relativity seems to allow it to be destroyed in a singularity. This contradiction has led to the creation of new theories, such as the holographic principle. According to it, all the information that falls into a black hole can be encoded on its event horizon. This information exists as a kind of hologram record that reflects the entire content of the black hole. Every black hole in the universe has its own history. It can occur due to the collapse of a massive star or the merger of smaller black holes. A merger is an event of colossal proportions in which energy equal to the mass of several suns is released in the form of gravitational waves. These waves are a kind of cosmic ricochet that travels through spacetime, carrying information about the masses, rotations, and distances of black holes that have merged. Gravitational waves ushered in a new era in astronomy. They allow us to explore objects that we would never be able to see with traditional methods. For example, thanks to gravitational waves, we can detect black holes that do not interact with matter and therefore remain invisible in conventional telescopes. This makes it possible to create a more complete picture of how black holes are distributed in the universe and how they affect its evolution. The regions of curvature of space and time also pose us with questions about other dimensions. Imagine that our three-dimensional spacetime is just part of a larger, multidimensional universe. Black holes can be a kind of windows into these extra dimensions, although these ideas so far remain speculative. However, they stimulate the development of theories, such as string theory, which tries to unify all the fundamental forces of nature into a single concept. Even centuries after Einstein predicted the existence of black holes, they remain an object that inspires, surprises, and forces you to look for answers to questions that seem unsolvable. What is hidden behind the event horizon? Can we ever look inside without destroying ourselves in the process? And will black holes ever be able to become our allies in trips to the farthest corners of space? These questions may remain unanswered for many years to come. But this is precisely the greatness of science, it never stops searching, even if the answers seem unattainable. Black holes are a reminder that human curiosity and the desire for knowledge have no limits. They are a challenge that pushes us to discovery, and at the same time a door into infinity that we are just beginning to discover. Black holes, as incomprehensible and mysterious phenomena, continue to fuel our imagination in science, opening up new horizons of understanding for humanity. They are the gateway to the deepest cosmic mysteries and may prove to be the key to solving fundamental questions about the nature of the universe. One of the most striking characteristics of black holes is their ability to warp the space and time around them. This distortion is so strong that even light cannot escape its influence. Imagine a beam of light passing near a black hole. Instead of a straight line, it forms a curved trajectory, creating a gravitational lensing effect. Thanks to this effect, we can observe distant galaxies that would otherwise be invisible. The black hole acts as a kind of cosmic lens that magnifies the image of distant objects and allows you to look into the depths of the universe. Imagine another exotic situation, an object that crosses the event horizon of a black hole. From the point of view of an external observer, this object will never reach the event horizon. It will appear frozen in time, turning more and more red until its light goes out completely. But from the point of view of the object itself, time will pass of course, and it will quickly fall into a singularity, where the laws of physics that we know cease to apply. The singularity is the central element of a black hole, a point of infinite density and curvature of spacetime. This is where the theory of relativity ceases to be applicable and there is a need to create a new theory that could describe these extreme conditions. Quantum gravity, which combines quantum mechanics and the theory of relativity, is one of the main contenders for this role. However, its development remains one of the biggest problems of modern science. Another aspect that makes black holes so fascinating is their relationship to thermodynamics. Imagine that black holes have temperature and entropy, as predicted by Stephen Hawking. The entropy of a black hole is proportional to the area of its event horizon, which opens a window to deeper connections between information, quantum processes and gravity. This begs the question, can the universe be a kind of giant information system, where black holes play the role of a kind of quantum servers that store and process information? Some scientists have suggested that black holes could be gateways to other universes. If an object passes through the event horizon, it may not just disappear, but enter a new spacetime, completely different from ours. These theories remain speculative, but they offer interesting opportunities for reflection on the multidimensionality and complex structure of reality. Another prospect is the use of black holes to investigate the quantum nature of gravity. For example, Hawking radiation shows that black holes are not completely black. They emit faint thermal radiation due to quantum effects at the event horizon. This phenomenon, although very slow for massive black holes, could prove critical for understanding the interaction of gravity and quantum fields. No less intriguing is the idea of the existence of primordial black holes that could have arisen immediately after the Big Bang. If they exist, these black holes could be responsible for many phenomena that we don't yet understand, such as the nature of dark matter. Primary black holes can have masses ranging from very small to very large, and studying them can shed light on the early history of the universe. Modern technologies such as the LIGO and Virgo gravitational wave observatories have ushered in a new era in the study of black holes. Thanks to gravitational waves, we can observe events that were inaccessible before, collisions and mergers of black holes, interactions between them, as well as their impact on the surrounding space. These observations allow us to create more and more accurate models of their behavior and impact on the cosmos. Black holes are the place where time stops, matter disappears, and the unknown begins. They demonstrate that the universe is much more amazing than we can imagine, and that each discovery brings with it even more questions. They are a challenge to science, philosophy, and our imagination. They symbolize that even in the darkest corners of space there is something that it is worth studying, something that can change our understanding of reality. Black holes are the keys to infinity that we are just beginning to comprehend. Black holes remain an eternal mystery that humanity is trying to solve, and each new look at them opens up even deeper horizons. They are not only objects of extraordinary power, but also symbols of the absolute limits of our knowledge. Studying black holes is more than just astronomy, it is the search for answers to fundamental questions about the nature of reality, the universe, and our place in it. Imagine a universe where black holes act as a kind of cosmic conductors. They control the distribution of matter and energy, the formation of galaxies, and influence the motion of stars. Supermassive black holes, which are at the centers of galaxies, are the main drivers of these processes. Their gravitational influence is so strong that it is able to form the orbits of millions of stars, creating a stable galaxy structure. But that's only one side of their role. They can also destroy, by absorbing stars or ejecting powerful jets of matter that change the dynamics of the cosmic environment. The accretion disks that form around black holes are some of the hottest and brightest objects in the universe. As matter spins and falls into a black hole, it heats up to millions of degrees, forming a glow that is visible billions of light-years away. This glow can obscure the entire galaxy where the black hole is located, creating objects we call quasars. Quasars are among the brightest beacons in space and allow us to explore the far reaches of the universe, revealing its history. Even more surprising is the phenomenon of relativistic jets. These narrow streams of energy, which are ejected from the poles of the black hole, are the result of the complex interaction of magnetic fields and the rotation of matter in the accretion disk. Jets can penetrate intergalactic space millions of light-years away, affecting clouds of gas and dust from which new stars are formed. They not only destroy, but also create, regulating the processes of star formation and galaxy formation. Equally intriguing is the suggestion that black holes may be connected to other universes or dimensions. Imagine that there is something more lurking behind the event horizon than we can imagine. Some theorists suggest that black holes may be wormholes, tunnels that connect different parts of spacetime or even different universes. Although this idea is speculative for now, it makes us reflect on how complex the structure of reality can be. Modern technology allows us to explore black holes more and more deeply. In 2019, the world first saw an image of the shadow of a black hole's event horizon thanks to the Event Horizon Project telescope. This was a confirmation of many theories and showed how far we have come in the study of these objects. But this is just the beginning. In the future, more powerful telescopes and gravitational wave observatories will make it possible to study even more details, such as rotation, interaction with surrounding matter, and even possible quantum effects. Black holes also pose fundamental philosophical questions to us. What is time? Does it have a beginning and an end? Is spacetime continuous, or does it break down into quanta under extreme conditions? Black holes, with their ability to slow down and even stop time, challenge our usual perception of reality. Imagine that time could flow very differently for objects that are near the event horizon than for those observing from afar. This reminds us that our ideas about reality are only part of a much more complex picture. They also make us think about the nature of information. What happens to information about objects that fall into a black hole? Does it disappear forever, or is it preserved in some way? The holographic principal hypothesis assumes that all information can be encoded on the surface of the event horizon in the form of a two-dimensional record. If this is the case, then black holes are not just objects, but something like cosmic hard drives that store data about the universe. Black holes, for all their mystery and incomprehensibility, are a source of boundless inspiration. They symbolize the idea that the universe is much more complex and interesting than we can imagine. They remind us that each new discovery is just the beginning of a new journey in search of truth. Black holes are a window to infinity that makes us ask questions, look for answers, and never stop marveling at the immensity of space. Black holes remain a source of endless mysteries and scientific discoveries, and the more we investigate them, the more interesting details and unexpected finds are revealed to us. One of the most interesting phenomena associated with black holes is the process of forming gravitational waves. When two black holes merge, they create waves in spacetime itself that propagate at the speed of light. In 2015, it was possible to record these waves for the first time using the LIGO observatory. It was a revolution in physics. Gravitational waves allow you to hear space, observe events that remained invisible before. For example, they can reveal the mass, rotation, and even distance to merging black holes. Another discovery is how black holes interact with the surrounding matter. Supermassive black holes that are at the centers of galaxies can affect the galactic climate. For example, energy emissions in the form of jets can heat gas in galaxies, inhibiting the formation of new stars. But this process also has the opposite effect. Some jets, on the other hand, can compress gas, which stimulates the formation of new stars. This is a kind of game of creation and destruction, where the black hole plays the role of a space architect. The study of relativistic black hole jets is also incredibly interesting. For example, in the galaxy M87, a huge jet stretching for thousands of light-years was observed. This jet of matter is ejected at close to the speed of light and emits radio waves that we can capture. Studying such jets helps to understand how black holes convert gravitational energy into high-energy particle streams. Another interesting area of research is attempts to detect primordial black holes. These are objects that could have arisen immediately after the Big Bang, when the density of matter in the universe was extremely high. They can have different masses, from a few grams to several solar masses. If they exist, it could explain the nature of dark matter, which makes up a large part of the mass of the universe but remains invisible to us. An interesting phenomenon associated with black holes is their connection with mysterious dark energy. Some researchers suggest that black holes may be sources of dark energy, which is responsible for the accelerated expansion of the universe. Although this idea remains hypothetical, it opens up a new direction in cosmology that combines the microcosm of quantum physics with the macrocosm of cosmic evolution. Another area of interest is the possibility of creating artificial black holes in the laboratory. Although it seems fantastic, microscopic black holes could theoretically arise during high-energy experiments, such as at the Large Hadron Collider. Such black holes would be unstable and evaporate rapidly due to Hawking radiation, but their creation could confirm many theories of quantum gravity. The study of the effects that black holes cause in their immediate surroundings cannot be overlooked. For example, at the center of our galaxy, the Milky Way, is the supermassive black hole Sagittarius A star. Astronomers observe the movement of stars near it to study its mass and behavior. One star, S2, orbits Sagittarius A** at an extraordinary speed, which confirmed the predictions of Einstein's theory of relativity. Also worth mentioning are supermassive black holes in other galaxies that form active galactic nuclei. Their behavior changes depending on how much matter they absorb. For example, when the accretion disk around a black hole is depleted, the core becomes less active and gradually falls asleep. This allows us to study the evolution of such objects and their impact on galaxies. Black holes are also objects of artistic inspiration and fantasies. Imagine an interstellar ship that uses a black hole as a source of energy or as a mechanism to accelerate in a journey through space. While such ideas remain in the realm of fiction, they are based on real-world physical principles, such as using gravitational maneuvers to gain extra speed. The study of black holes continues to change our understanding of the universe. They are not only a challenge for science, but also an inspiration for future generations of researchers who will seek answers to questions that seem almost unsolvable. Black holes remind us that the darkest corners of space can hide the brightest truths about our reality. Black holes are not just physical objects, they are among the greatest mysteries of the universe, combining the most complex aspects of cosmology, quantum physics and general relativity. They symbolize the limits of our knowledge and at the same time invite us to overcome them. By studying black holes, we not only expand the boundaries of science, but also face deep philosophical questions about the nature of reality, time and space. Each black hole tells its own story. They arise from the death of stars, are born in terrible cataclysms and absorb everything in their path. But despite their reputation as destroyers, they are also creators. They form galaxies, control the movement of stars, and even influence the evolution of the cosmos as a whole. Their accretion disks and jets are sources of incredible energy that can change the course of cosmic processes. Black holes are also laboratories where we test the limits of our theories. They allow us to study extreme conditions that cannot be created in terrestrial laboratories. They force us to look for new theories that combine quantum mechanics and gravity. They change our understanding of time, space, and information. Hawking radiation, the holographic principle, and the evaporation of black holes are all just the tip of the iceberg in the study of their nature. The future study of black holes promises to be even more exciting. New generations of telescopes and observatories will make it possible to study event horizons with unprecedented precision. Gravitational wave astronomy will pave the way for understanding the invisible aspects of the universe. And maybe someday we will even be able to create miniature black holes in laboratories, which will be a breakthrough in understanding quantum gravity. But like all great mysteries, black holes also make us look inward. They make us think about what cognition means and whether there are limits to this process. Will we ever be able to look beyond the event horizon and see what is now hidden from our eyes? Will we find a way to understand the singularity? Will black holes help reveal the secrets of the beginning of time and the evolution of the universe? Black holes are a mystery that never ceases to arouse fascination and curiosity. They symbolize the unknown and are a guide to new discoveries. Studying them is a journey that forces us to push the boundaries of what is possible, ask the most daring questions, and never stop searching for the truth. And even if the answers seem unattainable, the research process itself brings us more than we could have imagined. Black holes are a reflection of the infinity of the universe and our endless thirst for knowledge.